This is Euclid Book 10, proposition number 33, and we're going to start with a lemma that should have been put on Euclid Book 10, proposition number 32. And here's the diagram. Okay. It says, let ABC be a right-angled triangle having the angle A right, and let the perpendicular AD be drawn. I say that the rectangle CBBD is equal to the square on BA. Okay. So, we're first going to say that ABC is a right angle triangle, and angle A here is right angle. That's what we're going to say first. Then we're going to drop this perpendicular AD. I said that the rectangle CBBD is equal to the square on BA, the rectangle BCCD is equal to the square on CA, the rectangle BDDC is equal to the square on AD, and further, the rectangle BCAD is equal to the rectangle BAAC. Now, if you're confused, don't worry about it. We'll get into this. And first, the rectangle CBBD is equal to the square on BA. For since in a right angle triangle, AD has been drawn from the right angle perpendicular to the base, therefore the triangles ABD and ADC are similar both to the whole ABC and to one another. And this is by Euclid Book 6, proposition number 8. What are they saying there? I know I've been going through a lot of letters here. Let's go into this. Okay, we have the triangle. Okay. So we have triangles ABD. Well, here's ABD right here. That's this triangle right here. And then we also have ADC. This one right here. So these two triangles right here are similar to each other. And they're also similar to this great big one right here. So they're similar to each other and also similar to the whole thing. Okay. And since the triangle ABC is similar to the triangle ABD, therefore as CB is to BA, so is BA to BD. Okay. Guess we better write this down. Okay, so now we have formed a ratio, just like this. Where do we get the lines? This is CB right here. This is AB right here. Again, this is AB right here. And this is BD right here. And that's the ratio. Okay? And this is by Euclid Book 6, proposition number 4. Therefore, the rectangle CBBD is equal to the square on AB. So, if we were to form a rectangle with two sides this length and two sides this length, the area inside of that would be equal to the square on this. In other words, if we took this line and formed a square out of it, then that rectangle we formed previously would have the same area as this. Okay. For the same reason, the rectangle BCCD is also equal to the square on AC. Okay. So, the rectangle that's formed by CB and BD has an area that's equal not only to this area if we formed a square out of it, but also this area when we form a square out of it. Okay, so we're going to form a square out of this line and form a square out of this line, and this area are equal to that rectangle which we talked about before. Okay? And since, if in a right-angled triangle, a perpendicular be drawn from the right angle to the base, the perpendicular so drawn is a mean proportional between the segments of the base, which is by Euclid Book 6, proposition number 8, porism. Alright, so we're going to form another ratio. As BD is to DA, that's the first part of the ratio, so is AD to DC. So is AD to DC. Therefore, the rectangle BDDC is Therefore, the rectangle BDDC is equal to the square on AD, and this is by Euclid Book 6, proposition number 17. What does that say? Okay, we have to make a rectangle. We have two lines to make that rectangle out of. BD and DC. So we're going to take this line right here, we're going to take this line right here, we're going to form a rectangle out of it. Okay? And then we're going to form a square out of AD. See this line right here? We're going to make a square out of it. So the rectangle formed by this line and this line will have an area equal to the area that is formed out of this square. That's what it's saying. I say that the rectangle BCAD is also equal to the rectangle BA and AC. So, now we're going to say that if we take BC right here, and we take AD right here, we make a rectangle out of these two lines right here, and we can do that, that the area inside of that particular rectangle is going to be equal to another area. What other area is that area going to be equal to? Well, it's going to be equal to BA and AC. So in other words, we are going to form a rectangle out of this line and this line. Okay? So you're going to take this line and this line, you're going to form a rectangle out of it, and the area out of that will be equal to the other area that we were talking about a minute ago. For since, as we said, ABC is similar to ABD, which is by Euclid Book 6, proposition number 4, therefore as BC is to CA, so is BA to AD. Okay? As BC is to CA, so is BA to AD. Okay. Therefore, the rectangle BCAD is equal to the rectangle BA and AC. And this is by Euclid Book 6, proposition number 16. So, we take BC and AD and we make a rectangle out of it. The area inside of that rectangle is going to be equal to something else. What is that area going to be equal to? BA and AC. So we're going to take these two lines, we're going to form a rectangle out of this line and this line, and the area inside of it is going to be equal to the other area we were talking about a minute ago. And that's the lemma. Now, what about the next proof? Alright, so now we're going to present Euclid Book 10, proposition number 33, for real. Okay, here's the proof. To find two straight lines, incommensurable and square, which make the sum of the squares on them rational, but the rectangle contained by them medial. Let there be set out two rational straight lines, AB and BC. Okay, so AB is a rational straight line, so is this. They're commensurable and square only. and such that the square on the greater AB is greater than the square on the less BC by a square on a straight line commensurable with AB, which is by Euclid Book 10, proposition number 30. Okay. But BC is bisected by D. Okay, we're going to take the line BC right here, we're going to bisect it by this line right here, or this point. Okay. Let there be applied to AB a parallelogram equal to the square on either the straight lines BC, BD, BDC, and okay. Okay, so we're going to apply on AB a parallelogram. And this parallelogram is going to have the same area as either BD or DC. So you have your choice on this. You can either form a square by the length of BD, or you can form a square by the length of DC. And the reason for that is because BD is exactly the same size as DC. This is as long as this. We bisected BC, so these two lines are exactly the same length. So we can form a square out of this, or we can form a square out of this. Okay. And let it be the rectangle AEEB. Okay, so we have the rectangle AEEB, but you just don't see it. Okay, so we're going to form a rectangle out of this line length and this line length. All right. So two sides of the rectangle are going to be this, and two sides of the rectangle are going to be this. And the area inside of that rectangle will be the same area as if you formed a square out of this or a square out of this. Okay. Now we're going to describe a semicircle. What we're going to do is we're going to draw a semicircle. That's what we've done here. Okay. And this is by Euclid Book 6, proposition number 28. And let EF be drawn at right angles to AB. Okay. So we draw EF like this, and it's at right angles to AB. And that's how we got AE and EB. And let AF and FB be joined. Okay, so we drew a line from A to F, and then we drew another line from F to B. That's what we did. Okay. Then, since AB, BC are on equal straight lines, and the square on AB is greater than the square on BC by the square on a straight line incommensurable with AB, so in other words, if you take this line here and you square it, and you take this line here and you square it, then this square is going to be this bigger than this square by some square of a line that is incommensurable with this, with AB. Okay. While there has been applied to AB a parallelogram equal to the fourth part of the square on BC, that is to the square on half of it, deficient by a square figure making the rectangle AEEB, therefore AE is incommensurable with EB. This is by Euclid Book 10, proposition number 18. So, there is no number that will measure both this and this. That's what Euclid's saying. Let's go on here. And as AE is to EB, so is the rectangle BAAE to the rectangle ABB. Okay. So as AE is to EB, so now we're going to form a ratio. The first part of it is AE to EB. Then we're going to form two rectangles. Rectangle number 1, okay, is BAAE. Okay, so what we're going to do is we're going to take this line length and this line length, and we're going to form a rectangle out of it. And then we're going to form yet another rectangle. And it's going to be AB and BE. So the next rectangle we're going to form is AB and BE. Now we have to make a ratio. Let's make the ratio. Okay, there's your ratio right there. Okay. While the rectangle ABAE is equal to the square on AF. Okay. So now what we're going to say is so we're going to take the rectangle that you're going to form a rectangle AB and AE. So you're going to take this line, you're going to take this line, you're going to form a rectangle out of it. The area inside of that rectangle is equal to the area in AF. What is AF? This is AF right here. So you're going to form a square out of it, and the area inside this rectangle is going to be equal to the area inside this square. Okay. Oh boy. Now all you have to do is change some letters. Okay. So now we're going to say that this rectangle, which is formed from this line and this line, will have the same area as this square. Now where did this square come from? Right here. You're going to make a square out of this line right here, and that area is going to be equal to that one. Okay. Let's go on. Therefore, the square on AF is incommensurable with the square on FB. So, if you take this line and make a square out of it, the area inside of there is incommensurable with the square you'll form from this line. Therefore, AF and FB are incommensurable in square. Okay. And since AB is rational, therefore the square on AB is also rational. So if this line is rational, so will its square be rational. So the sum of the squares on AF and FB are also rational. So, if we make a square out of this line and a square out of this line and we add the two areas together, they will be rational. Because their sum is the sum of the square on AB, which is by Euclid Book 1, proposition number 47. Okay. And since, again, the rectangle AEEB is equal to the square on EF, here we go again. More confusion. Okay, so we form a rectangle, two sides will be this length, two sides will be this length, and then we form a square, and all four sides of that square will be this length. So the area in this rectangle is going to be equal to the area in this square. Okay. Hold on. I think my marker died. Not to worry. We'll just use a green one. See this marker? Well, that missed the trash can. You want to see an instant fail? There was an instant fail. Okay. And by hypothesis, the rectangle AEEB is also equal to the square on BD. Okay, so now we got AEEB. We have formed a rectangle out of that. And now it is equal to the square on BD. Okay. Therefore, EF is equal to EB. I'm sorry, that's incorrect. EF is equal to BD. So now we can say that the length of EF is equal to the length of BD. Therefore, CB is double of EF. This line here is double the length of this line right here. Why? Because if this length is equal to this length and this length is half of this length, then this length is going to be double of this. That's what we can say. So that the rectangle ABBC is also commensurable with the rectangle ABEF. Okay. I wish they wouldn't do this. So now they're going to say, or Euclid is saying here, that if you formed a rectangle and two sides of it was the length of AB and two sides of it was the length of BC, then that particular area is commensurable with a rectangle that is formed by two lines of this and two lines of this. That's what Euclid's saying. Okay. But the rectangle ABBC is medial. This is medial. And that's by Euclid Book 10, proposition number 21. Therefore, the rectangle ABEF is also medial. And that's by Euclid Book 10, proposition number 23, porism. So if this is medial, so is this. Okay. But the rectangle ABEF is equal to the rectangle AFFB. So we're going to take this line right here, we're going to take this line here, we're going to make a rectangle out of it, and that rectangle is equal to this rectangle. And that is by the lemma we just talked about maybe 15-20 minutes ago. Therefore, the rectangle AF and FB is medial. If these two are equal, and that's medial, so is that. Okay. But it was also proved that the sum of the squares of these straight okay, let me say that again. But it was also proved that the sum of the squares on these straight lines is rational. Therefore, two straight lines, AF and FB, okay, incommensurable and square, have been found which make the sum of the squares on them rational, but the rectangle contained by them medial, which is what we were trying to prove. Wow, what a long proof. Hope I don't have to do that one again. I will tell you more in a future video. Stay tuned.